Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW English. So, yes, my dear students, today we are going to start with our lecture number 3rd based on the chapter Coordination Compound under our batch Excellence Batch. So, students, before starting this lecture, let me tell you one thing. Whether you are preparing for any examination or you are studying any topic and you feel like there is a lot of syllabus you need to do and there is very few time left for that examination, just try to give your best, because if you try to give your best, then you will never have to wonder about what you could have done if you have summoned all your thunder, and if your best was not as good as you hoped it would be, you still could say, I gave today all that I had in me. So trust yourself and give your 500% to the topic. And if you still fail, students, you will feel this thing that yes, I gave my best. Now, rest I will leave it to the God. Okay? And see, when you give your best, when you do a lot of hard work, you will automatically see the results. And results, they won't come in a day. It is day in and day out practice that you need to do by your own. Yes? So, little efforts will lead you to a huge success, to a beautiful, a tasty fruit that you will get in return. So, keep working hard. Now, we shall start with this quote, our today's session, that is going to be lecture number 3rd. I hope so you have seen the previous lecture and you are able to now name the coordination compounds. We have covered the naming section of the coordination compounds in the previous lecture. So today we are going to study about the theoretical section with regard to what is Werners Theory and what is valence bond theory with respect to coordination compound. So first of all, students, in today's session, what are the topics that we are going to cover? So the very basic topic that we are going to cover today will be about Werner coordination theory. Then you are going to understand about valence bond theory. Now students, this particular lecture and the lecture that you are going to do after this, they both are really very important. See, this session you may feel easy because you have already understood what is basically oxidation number and what do you refer to as coordination number. These two terms are going to be used in this particular topic, that is Werner's coordination theory. Now let us see that what does this scientist Werner explain us. Basically, if I ask you who was the father of coordination chemistry, so the father of coordination chemistry is Werner, right? So the father of coordination chemistry is scientist Werner. Now students, what Werner told in his coordination theory? He explained the theory that it basically contains two kinds of valencies. Now understand this very simple concept. He explained that there are two kinds of valencies. Now, what are the two kinds of valencies that are exhibiting in the coordination compounds while we are observing a coordination compound? What are the two basic valencies? The very first that you shall observe over here is the primary valency. Which one? Primary valency. And if I talk about the second one, it is basically which one? Secondary valency. Now, what is primary valency and secondary valency? Werner explained that primary valency is the another term used for oxidation number, while the secondary valency is the another term which is exhibited for coordination number. What Werner said? Werner said that it exhibits, primary valency exhibits about oxidation number About what? About oxidation number. And if I talk about secondary valency, secondary valency exhibits what? Coordination number. It exhibits coordination number. Now, students, before moving on to the next part, with respect to Werner's coordination theory, let us revise about oxidation number and the coordination number by taking a certain example over here. Okay, if I take this particular example over here, that is CONH3 6Cl3. Now just tell me what will be the oxidation state for the central metal atom. Now as you can see, this is a coordination compound. How it is referred to as a coordination compound? My question arises. Now you can say that, ma'am, over here, what do we observe? We observe that this is basically our central metal atom. What it is? It is central metal atom. Am I right? Yes. Okay. The very next thing that we observe over here, ma'am, is these are the ligands that are present over here. These are the ligands. NH3, basically, there are 6 ligands that are present over here. This 6 denotes number of ligands that are present. Am I right? Now, these are ligands that are forming a coordinate bond with whom? With central metal atom. And what else do we observe over here? We observe over here, ma'am, these 3 chlorine ions. Now, what are these ions? These are ionizable ions. Which ions? Ionizable ions. Am I right? Yes, ma'am. Okay. These are ionizable ions. Now, coming back to the part about primary valency and the secondary valency. If I talk about that, what is the oxidation state? I hope so you all have calculated the oxidation state of the cobalt over here. How do we calculate the oxidation state? Now let us move on to the next slide. But before going on, I want you all to write it down. Okay? Write it down for a minute. You can pause the video and just write it down. Now moving on to the next part. Just kindly see. Okay. See, basically, I gave you this case where we have CO, NH3, 6 and we have Cl3. Am I right? Now see, in order to calculate the oxidation state or the oxidation number, oxidation state or oxidation number is the same thing, right? Now, if we need to calculate the oxidation state for cobalt, we need to let the oxidation state for cobalt as what? X. Now, X plus. What is the, charge on ammonia, NH3? What is the charge on that? Basically, it is neutral. It has no charge, a 0 charge. So, it shall be 0 into how many ammonia? 6. Now, we shall add this Cl basically holds -1 charge. Yes, ma'am. How many Cl? 3. Their sum shall be equivalent to 0. Now, I have already told you, in order to calculate the oxidation state, there are 2 methods that you can apply. This is the very first initial method, that you can just add all the oxidation states of all the elements that are present in a particular compound and you shall put them equivalent to 0. There is one more, way in order to calculate the oxidation state. I shall tell you that same over here. See, what is that? For cobalt, you need to calculate. So, let it as X. Now, for ammonia, it is 0 because it is neutral in nature. How many ammonia? Ma'am, 6 ammonia. Now, basically, when we talk about this particular, compound, when I dissociate into its ions, when I dissociate this particular compound into its ions, what are the ions I'm getting over here? I shall get CO, NH3, 6, -3 plus 3Cl negative. Am I right or wrong? Just tell me one thing. You know that Cl holds -1 charge. Yes, okay. So, we know that the ions or the atoms that are present inside the coordination sphere. This is what? This is basically, this square bracket represents your coordination sphere. Am I right? Now, the atoms or the ions that are present inside the coordination sphere, they basically won't ionize. They are non-ionizable ions. These inside ones, these basically are the non-ionizable ones. the non-ionizable ones, while this is the ionizable one. That means the non-ionizable one shall remain same and the ionizable one will come out. Am I right? Now over, see what is happening. This will remain as it is, and we know that Cl holds -1 charge. So we have Cl negative over here. How many Cl atoms, ma'am? 3 Cl atoms. So 3 Cl negative will come. Now if basically it is a neutral species, a neutral species holds equivalent positive charge and equivalent negative charge. So what are we getting over here? We are getting -3 charge. So in order to balance -3 charge, we shall bring which charge? +3 charge. So which charge will arise over here? Sorry, kindly correct it. +3 charge. So which charge will come over here? +3 charge will come over here. Is it clear? Now in order to calculate for this, we know for cobalt it is let us X. For ammonia, neutral species, so 0 into how many ammonia? 6 is equivalent to the total charge on the species, that is +3. Now what shall we get? X plus 0 is equivalent to +3 and X comes out to be +3. Over here, if you need to calculate with this particular method, just kindly add all the oxidation states, all the charges of the elements present in the compound, and that will be equivalent to 0. Now over here, if you see, it is X plus 0 minus 3 is equivalent to 0. When you take this -3 on to the next side, what you shall get? X is equivalent to +3. So both are the methods which you feel comfortable, you can follow them. Now this +3 is the oxidation state that is present on the central metal atom. Am I right? So I told you that primary valency exhibits oxidation state. Am I right? So if I ask you what is the primary valency for this particular compound, you will say that, ma'am, primary valency is the another name for oxidation state. So over here in this particular compound, the primary valency comes out to be +3. Now, if I ask you students, what is the secondary valency in this particular coordinated compound? You will say that, ma'am, the secondary valency is exhibited by the coordination number. What is coordination number? Coordination number is basically the number of ligands, or I would say the number of donor atoms that are present in the particular species, or I would say the number of coordinate bonds that are being formed in a coordination compound. So if I come back to this particular structure over here, what I observe that basically there are 6 ammonia, and in this 6 ammonia we have nitrogen as the donor atom. That means 6 nitrogen are donating their lone pair of electrons to the central metal atom, and they're forming which bond? They are forming a coordinate bond. So what will be the secondary valency in this case? The secondary valency, ma'am, the secondary valency will come out to be 6, because there are 6 donor atoms that are present in this particular coordinated compound. Is it clear to you? Now kindly write it down. I will explain you a major difference between primary valency and the secondary valency. I hope so. Now this is clear to you people. Right? Okay. Now moving on to the difference between the primary valency and the secondary valency. Kindly understand this concept. After that we shall read the NCERT also. On one side you can write primary valency. On one side you can write primary valency, and on the another side you shall write secondary valency. You will write which valency? Secondary valency. Now understand the very basic difference between both of them. Let us see the very basic difference. See, if I talk about primary valency, you can say it is exhibited, the very first point, exhibited by whom? Ma'am, it is exhibited by oxidation state or the oxidation number. Oxidation state or oxidation number. Am I right? Now if I talk about secondary valency, students, exhibited by coordination number. Exhibited by what? Exhibited by coordination number. Now the next most important things that we can say that primary valency, basically which ions are responsible for primary valency? Ionizable ions. Now this is really very important thing. And which ions are responsible for secondary valency? Non-ionizable ions. Ma'am, how can you say that? Kindly explain with a certain example. Now understand this very basic concept. Okay. I'm writing over here. Okay. I am writing the same compound over here. It is CONH3 6 and then we have Cl3. Now see over here, if I talk about the ionizable ions, which are the ionizable ions? Ma'am, this Cl3 are the ionizable ions. Okay. These ionizable ions are responsible in order to calculate the oxidation state. You have just calculated the oxidation state over here. See, with the help of the Cl3, you generated a charge on it as +3 and you calculated with the help of this charge the oxidation state. Or just forget this method and come back to this method and see, you are also taking this Cl3 charge over here. That means ionizable ions are responsible and are helping you out in order to calculate what? In order to calculate the primary valency. So ionizable ions are responsible for calculating what? For calculating your primary valency. So the second point over here is ionizable ions. Ions are responsible. Ionizable ions are responsible for calculating primary valency, or I would say the 1 degree valency. It is the same thing. Okay, and over here if I need to write, what I shall write over here? Non-ionizable ions are responsible for secondary valency or the 2 degree valency. Is it clear to you? How non-ionizable ones? Ma'am, kindly explain this also. See, okay, this we can see over here only in this particular example. See, here secondary valency basically is the another terms for coordination number. We say secondary valency is the coordination number. Now coordination number is basically what? It is talking about ligands or the donor atoms. The same thing. That means here we are talking about what? Here we are talking about ligands. So ligands basically are present inside this square bracket in this coordination sphere, in this coordination entity. That means the ones which are present inside the coordination sphere or the coordination entity are the non-ionizable ones. Just see over here. I've written the non-ionizable ones are the present which are present inside the coordination entity or the coordination sphere or the coordination complex. Now over here, the ones that are present inside and are responsible for coordination number 1 are the ligands. So here we can say that these are the non-ionizable ones which are responsible for causing the secondary valency. Now one more thing students, if I talk about primary valency, it does not help us to determine the geometry of the coordination compound. While if I talk about the secondary valency, it is responsible for depicting the geometry of a certain complex. So the next I can say over here, the third point, it does not depict geometry of the complex. Now if I talk about which one, the secondary valency, the third point, sorry, it helps in depicting the geometry of the coordination complex. Now other than this students, one more thing that you need to know, the fourth point and the last point. If I talk about the primary valency, it is non-directional in nature. It is non-directional in nature and is represented by dotted lines. I'll let you know with a certain example, you will get to know. So you can write they are non-directional in nature and they are represented by which? By the dotted lines. Now coming back to the secondary valency, it is directional in nature and it is represented by a solid line. Okay. So the fourth point over here, it is directional. It is directional in nature and represented by solid line. Which line? The solid line. Kindly write it down, students, so that we can move on to our next part. I want you all to write it down once. Kindly write it down. It is non-directional in nature and represented by dotted lines. It is directional in nature and represented by the solid line. I'll give you a certain example explaining the fourth point over there. But I guess all the 3 points, the very first 3 points are clear to you, right? Even the third point will be explained in a certain example. Let us see the example now. Let us understand about the example further. See, now I am taking this example over here again, that is CONH3 6 dot Cl3. Now students, understand this very basic concept. We have just calculated the oxidation state. Oxidation state came out to be +3. I will be letting you in the coming sessions over there that when the oxidation state is referred to as +3, the coordination number comes out to be 6. Okay, over here if you see, the coordination number will be 6. Now there are certain oxidation state for which the coordination number values you generally learn out. For example, if I'm saying if the coordination number is +3, if the oxidation state is +3, so the coordination number over here, when you will calculate, I'll let you know in the coming segments, it comes out to be 6 over here. So what is happening? If we have coordination number 6, then we shall obtain its geometry and how it will look like. See, if we have the CO over here, there will be NH3 like this, then there will be NH3 like this. Yes, they all are ligands, so they are donating the lone pair of electrons over here like this. Over here we have again NH3, and here also we have again NH3, and here we have the fifth one, and here is the sixth one. So this is the representation of the ligands, that means of the secondary valency. They are represented by the solid line, the straight line. Now coming back to the Cl, we have to show these 3 Cl also. They are written like this with the dotted lines. Cl, Cl, okay, Cl, like this. Understand what I'm going to show you over here. I said you that the primary valency, that means the oxidation number, that means the ionizable lines, are represented by which lines? By the dotted lines. Is it clear to you? Now coming back to the again segment of the secondary valency. Secondary valency is the coordination number or the non-ionizable lines. Now see, now you're correlating all the terms. Yes, or the non-ionizable lines, they are represented by what? By solid lines. I would say the straight lines. Okay, while these are the filled lines, but they are the dotted ones. So this depicts the geometry of that particular compound. Is it clear to you all? Now taking one more example to let you know how these there is a very different case that you shall see over here. What is that different case? See, if I give you, certainly I'll give you CO. Let us take an example, Cl3.5NH3. Let us take this case. Now, if I ask you for this particular compound that we need to calculate the, first of all, what we shall do, we will calculate the oxidation state of the central metal atom. Central metal atom here is cobalt, again X. Now, what is the oxidation number for chlorine? We know the oxidation state of the charge on the chlorine atom is -1. Am I right? So, -1 into how many chlorine? Ma'am, 3 chlorine. Plus, we know that for ammonia, it is 0 charge. How many ammonia? 5. So, their sum shall be equivalent to 0. Yes, this is the way. Now, here, it will be x plus -3 is equivalent to 0. Now when this -3 will go on to the another side, it will become positive. X shall come out to be +3. So over here, the oxidation state or the oxidation number comes out to be +3. Am I right now? Okay, that's great. Again, I've told you just right now that when the oxidation number or the charge on that particular central metal atom comes out to be +3, the coordination number shall be 6. Now you just have got to that coordination of 6. So how you will, first of all, you will make a coordination compound. How you will make a coordination compound? In order to build a coordination compound, you require square brackets. Yes, ma'am. You require central metal atom. Yes, ma'am. You require the ligands over here. Now you shall know that in case of ammonia and Cl3, now I'll let you know, there is a strong field ligand and there is a weak field ligand in the coming cases. So we will be inserting ammonia over here. And how many ammonia will come? 5 ammonia are there. But we have just understood that coordination number will come out 6 at the oxidation number +3. But here only you are showing 5. basically five, I would say, the ligands, the five donor atoms, but we require six donor atoms. So one Cl will come inside. Hence, one Cl and five NH3. That means total six donor atoms are present. How many Cl will be left? Two will be left. So two will come as an ionizable one. Are you getting my point? What I'm saying? In the previous case, for example, the previous case was like this: COCl3.6NH3. Now again, if you calculate the oxidation number, X plus minus 1 into 3 plus 6 into 0 is equivalent to 0. X will come out to be what? Plus 3. Again, for this plus 3, coordination number is 6. So in order to generate a coordination compound, you shall write first of all the central metal atom. Then you require number of ligands. You will write ammonia. I will let you know why we have not written Cl inside first. Why we have written NH3. Because in the upcoming segments, you shall learn about the strong field ligand and the weak field ligand in the topic valence bond theory. So you'll automatically get. Now we know that coordination number should be 6. That means 6 ligands should be present. So over here 6 are there. So yes, this 6 is full. So these 3 Cl are left. So they will come out as the ionizable ions. But in this particular case, we have 5 NH3. If we have 5 NH3, but we require 6 ligands, in order to make coordination number 6, we require 6 ligands. So if the space is occupied by 5 NH3, then 1 Cl will come inside and the rest 2 Cl will go outside. So what shall we get over here? You shall observe that, ma'am, this is the formula of the compound being formed. Now if I have to show the geometry for both of the cases, in order to see the geometry for these cases we have just done right now, this is CO, this is going to be NH3, here this is going to be NH3, this is the third one because there are total 6 NH3, no? And in this NH3, nitrogen is responsible for donating its lone pairs of electrons like this. So they are represented by solid lines. Which one? The coordination number 1, because they are the non-ionizable ones. So they are represented by the solid lines, or I would say the secondary valency. Right now I want to talk about the primary valency, that is the ionizable ones. They are represented like this with the dotted ones. There are 3 Cl, so I have shown like this. This is the geometry for this particular coordination compound. Now coming to the geometry for this particular coordination compound, how we will show this, just observe over here. This is CO over here. How many NH3? 5 NH3. Okay, let us say this is the first NH3. This is second, in which nitrogen is, donating its lone pair of electrons. Then we have here as third. Then we have fourth. And then we have 5. Now we have 1 Cl also. So this is Cl that is written over here. Right? Now these were which one? These were the These were which? These were the secondary valency or the coordination number or the non-ionizable one. Now we will represent this Cl2. So you will write like this. This is Cl and this is Cl. Is this geometry correct? No, ma'am. Is this geometry correct? No, ma'am. Why, ma'am? My question is why, ma'am? This is still incorrect. Why? Because see, oxidation number was being calculated with the help of all of these 3 Cl. Are you getting my point? Oxidation number was being calculated by all of these Cl3, in which we saw that 2 Cl came outside, but 1 Cl is still present inside. Yes, so that means this Cl that is present inside is the responsible in order to calculate the oxidation state. Yes, it was responsible. Now you will say, ma'am, ammonia is also responsible. Why ammonia is responsible? Ammonia is holding no charge. Ammonia has 0 charge. So basically it has no value over here. And if it has no value in order to calculate the oxidation state because it has 0 charge on it, that means Cl is the only one who is responsible for creating a charge on the central metal atom. Am I right? Now, if Cl is responsible for creating a charge on the central metal atom, that means if this Cl is present inside, if it is responsible for creating primary valency, then primary valency is represented by dotted lines. Hence, here this Cl will also be written as like this. Both the lines will be shown over here. The solid one also as well as the dotted one also. Are you getting my point? And is it clear to you that why ammonia is not being shown by the dotted lines? Because students, ammonia is not responsible for causing any charge on the central metal atom. Ammonia here holds 0 charge, so it is not responsible, while Cl holds a -1 charge and it is responsible for creating the oxidation state on the central metal atom. Is it clear? I want you all to write it down, students, so that we can move on to the next part. I guess this is clear to you. Now you are clear with the term primary valency. Now you are clear with the term secondary valency. Let us start. Okay. Now let us read these lines from the NCERT. These are the lines from the NCERT. Let us understand about Werner's coordination theory. Okay, so it says that Alfred Werner, a Swiss chemist, was the first one to formulate his ideas about the structures of the coordination compound. In other terms, he is referred to as the father of the coordination chemistry, which I've already told you. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Now, Werner proposed the concept of primary valency and a secondary valency for whom? For the metal ion. Two kinds of valency he explained us. One is the primary valency and the second one is the secondary valency. Now see, binary compounds such as CrCl3, CoCl2 and PdCl2 have primary valency of 3, 2, 2 respectively. What is primary valency? Ma'am, primary valency is the oxidation state. Is what? Is the oxidation state. So you can calculate the oxidation state for all of these three over here. If I talk about CrCl3, here for Cr you will let as X. For Cl you know it is -1. How many Cl3 is equivalent to 0? So X shall come out to be +3. See, +3 is written. Now for the next one, CoCl2. Again for Co you will let it as X. For Cl you know it is -1. How many Cl2 is equivalent to what? Is equivalent to 0. Great. Okay. So X shall come out to be what? This will go over there. X shall come out to be +2. Similarly, if I talk about PdCl2, again you will let it as X. How many Cl? For Cl it is -1. 2Cl is equivalent to 0. X shall come out to be +2. So here what we have calculated, +3, +2 and +2 respectively, which they have already written over here. Is it clear? So you got to know that primary valency is basically the oxidation state in other terms. Yes. Now I'll see the next thing. Werner proposed the term secondary valency for the groups bound directly to the metal atom. That means the groups that are bounded directly to the central metal atom is referred to as whom? They are referred to as the ligands, or I would say they are the ones which are referred to as the donor atoms, I would say. Or in other terms, we can say they are referred to as the coordination number. They are referred to as the coordination number. We can use these three terms over here. See the line over here again. Werner proposed the term secondary valence for the number of groups bound directly to the metal atom. The ones that are bound directly to the central metal atom or which are donating the lone pair of electrons to the central metal atom are the ligands of the donor atoms or the coordination number. Is it clear to you people? Great. Now see the next line. In each of these examples, the secondary valencies are 6. In the previous cases, in the upcoming cases, you can see in the NCERT. Not in the previous case, in the upcoming case, you can see and you can automatically see the coordination number. Now, Werner in 1898 proposed this theory of coordination compounds. What was the theory? The main postulates. Now, this is really very important, students. You have to put a star mark over here. I have explained you. Now, I shall read all of them one by one. Let us see. Let us see this. Okay. Okay, let us see over here. In coordination compounds, metals show two types of linkages. Which one? Primary and secondary. Which kinds of linkages? Two kinds of linkages, primary and secondary. The next one. The primary valency are normally ionizable and are satisfied by negative ions. You can see the Cl negative. Cl negative. They are basically the normal ionizable ions and they are satisfied by the negative ions. Is it clear? The next thing. The secondary valencies are the non-ionizable ones. Non-ionizable ones are the coordination compounds or the ligands, I would say. Right? Now see, the coordination number, I would say, not the coordination compound, coordination number. Next thing. They are satisfied by the neutral molecules or the negative ions, I mean referred to as the ligands. Why they have written negative ions? Because negative ion holds lone pair of electrons and lone pair of electrons are the ligands which donate their electrons to the central metal atom. Now observe the next thing. The secondary valency is equivalent to the coordination number and is fixed for a metal. Secondary valency is fixed for a certain metal. For example, if you see the coordination number 6, you shall observe its geometry is octahedral. If you see the coordination number 4, you shall see the tetrahedral and the square planar geometry, which was explained by Valence bond theory, but not by the Werner theory. Werner was unable to explain about the geometry. Yes, it told us about the geometry with respect to, that yes, where ligands can be formed, where ions are being formed. But in the case, if I talk about which kind of geometry is being exhibited or what is the hybridization, that is explained by the valence bond theory. Now see, the secondary valence is equal to the coordination number and is fixed for the metal. The ions groups bound by the secondary integrated linkages to the metal have characteristic spatial arrangements corresponding to the different coordination number. They have a different arrangement. These are the postulates that were given by the Werner scientist. Now, in modern formulations, such special arrangements are referred to as coordination polyhedra. The complexes, they are referred to as coordination polyhedra. Now see, the species within the square bracket are coordination entities. Now this you have already seen in the previous lectures also. I've already told you. The species that are present within the square bracket are the coordination entities or the complexes, and the ions present outside are referred to as counter ion. This is really very important. See, basically, counter ions in other terms. Counter ions in other terms are the ionizable ions. So you can also say that counter ions are referred to as which ions? The ionizable ones, and they are present outside the square bracket. The ones which are present inside the square bracket are referred to as what? Are referred to as your coordination entity or the complexes. Now see, he further postulated that octahedral, tetrahedral and square plane geometry shapes are more common. It told you, but it was not able to explain the perfect geometry or the hybridization, I would say. But yes, it told that these are the the common examples. For example, they have given you over here that some of the geometry they have told you respectively. Great. Okay, students. Now moving on to the next theory comes the valence bond theory. See, I have told you already that Werner was unable to explain about hybridization. Werner was unable to explain about the magnetic moment. Werner was unable to explain about the magnetic properties such as paramagnetic, diamagnetic. So one more theory came into place, that is valence bond theory. Now let us understand what is valence bond theory. See, valence bond theory basically is very simple. What does it states us? That we have a central metal atom and we have certain ligands. Now what is the usage of or what is the role of ligands in this particular coordination compounds? In coordination compound, students, we know that ligands are the ones that donate their lone pair of electrons to the central metal atom. So what is happening over here? The ligands have a tendency to donate the lone pair of electrons to the central metal atom and they form the coordinate bond. Okay, one more thing that I've just forgotten over here. Let me tell you once again. Over here, students, in any of the case, in this particular case, let us understand this. You can see that there are two kinds of bond being formed over here. One bond is being formed between the ligands and the central metal atom. That is referred to as coordinate bond. The bond that is formed over here is referred to as what? Is referred to as a coordinate bond. But the bond which is formed between the counter ions or the ionizable ions and the non-ionizable ions, between ionizable and the non-ionizable ions are the ionic bond. Between these ions are the ionic one, and between the ligands and the central metal atom is the coordinate bond. Is it clear? Yes, ma'am. Okay. Now moving on to the valence bond theory. As I was telling you that the ligands are the one which are responsible for donating their lone pair of electrons to the central metal atom, hence forming a coordinate bond. So we can say that this is basically the structure. And how to represent it? We say that this is central metal atom, this is ligand, and these are the number of ligands like this, and we write the charge over here, positive and negative respectively. Yes, we do have ions over here, which we can see if it is a cation, it is written over here A positive, and if it is an ion, it is written over here as B negative. Great, it is like this. Now students, one more thing I want you all to understand. What does valence bond theory states that? Valence bond theory states that central metal atom provides vacant number of orbitals as per the coordination number of the complex. See, if the coordination number is 6, that means the central metal atom have a tendency to provide 6 vacant orbitals in order to form coordinate bond with that ligands. So, they provide the same number of vacant orbitals as per the coordination number. This is the very first thing that you understand in the valence bond theory. Now, the second thing that you understand in the valence bond theory is that the vacant orbital basically overlaps with the electrons of the ligand, forming a coordinate bond. Are you getting my point? Now let us understand over here with the help of the lines from the NCERT. What does it explains us? According to this theory, the metal atom or the ion under the influence of the ligands can use its N-1D, NS, NP or NS, NP, ND orbitals for hybridization. That means they are providing its orbitals in order to overlap and form a bond. Are you getting my point? Now see. To yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar and so on. So you shall observe these geometries over here. If you see the coordination number comes out to be what? If it comes out to be 4, students, the type of hybridization that you shall observe over here will be sp3. And yes ma'am, it will show a shape of tetrahedral geometry. Now, when the coordination number is again 4, one kind of geometry is again seen, that is square planar. But for that case, the hybridization will be dsp2. In the upcoming slide, I will let you know where you shall see the square planar geometry and where you shall see the tetrahedral geometry. Are you getting my point? So with the coordination number 4, we exhibit two kinds of geometry. One is tetrahedral, another one is square planar. For tetrahedral, the type of hybridization will be sp3, and for square planar, it shall be dsp2. Is it clear? Great. Very good. Now let's see, for the 5 coordination number, we have sp3d as the hybridization and the geometry is trigonal bipyramidal. Now let me tell you one thing. Generally, coordination number 4 and coordination number 6 are being asked in the examination. Generally, questions are asked from coordination number 4 and coordination number 6. So you don't have to skip both of them. They both are really very important. Now coming to the coordination number 6 over here, let us see. This is again really important. Coordination number 6, the geometry shall be octahedral, no doubt, but the hybridization can be different. One of the hybridization is sp3d2 and another one is d2sp3. Now, why the hybridization is quite different but the geometry is same for the case of coordination number as 6? Now, here students comes one more thing that valence bond theory explained us. Valence bond theory explained us about inner orbital complexes and outer orbital complexes. So, we got to know about these two terms over here. Moreover, valence bond theory also explained us about magnetic moment. Are you getting my point? So first of all, write all of these and do learn these. You will automatically learn with the certain examples which I will be telling you in the next slide. Is it clear? Now see, you can even mention over here, but before writing it, let us see the points again. These are the limitations, but before limitations, let me write what it explained us. So valence bond theory. So, valence bond theory explained about magnetic moment. It explained about magnetic moment such as, mu is the magnetic moment and it is n plus 2 Bohr magneton. It is the unit. So, over here n stands for number of unpaired electrons. N stands for number of unpaired electrons. Is that clear to you? Moreover, valence bond theory explained about paramagnetism or the paramagnetic behavior and the diamagnetic behavior. Now, what is paramagnetic behavior and the diamagnetic behavior? Paramagnetic behavior is seen when we see unpaired electrons. When there are unpaired electrons, we shall observe the paramagnetic behavior. And the diamagnetic behavior are seen when there are, paired electrons. When there are which electrons? The paired electrons. I want you all to write it down so that we can move on to the next part over here. Kindly write it down. Is it clear to you people? Now students, as I've told you, one more thing that the valence bond theory explained us was about the inner orbital complexes and the outer orbital complexes. So valence bond theory also explained about inner orbital complex inner orbital complex and outer orbital complex. Inner orbital complex and outer orbital complex. Now understand both of these terms. What is inner orbital complex? When the innermost orbitals are responsible for, making a bond, I would say, or are responsible for the overlapping by creating a bond. And when the outer orbitals are responsible, that shall be outer orbital complex. I will explain you with the example. Let us say we have a coordination number as 4. Now you know that basically when we have coordination number 4, it will exhibit two kinds of geometry. Which one? Ma'am, one is tetrahedral and the another one is square planar. Yes, ma'am. Okay. Now if I take a certain example, for example, I have nickel, then I have Cl4 and I have -2 charge. Let us say that we have this particular coordinated compound over here. Now understand, if I talk about nickel ground state electronic configuration. Let us talk about nickel ground state electronic configuration. It will be 3d8-4s2. What will be the electronic configuration when nickel is present in the ground state? It is 3d8-4s2. Now if I ask you what is the oxidation number when I am going to calculate with respect to over here, this central metal atom, here nickel is central metal atom, we will let it as x plus. For Cl we know charge is -1. How many Cl? 4. Overall charge is -2. So x minus 4 is equivalent to -2. We shall take this -4 over here. What we will get? We will get x is equals to -2 plus 4. X comes out to be what? +2. So the charge comes out to be what? Charge comes out to be +2. That means oxidation state came out to be +2. So if nickel is present in ground state and the electronic configuration, basically it's 3d8-4s2. So that means nickel when it will be present in +2 oxidation state. Nickel when present in +2 oxidation state, that means 2 electrons are taken out. So let us see that these 2 electrons are gone. What we will left over? We will be left over with 3d8. Now if I represent 3d8 over here, it is like this. We know there are 5 orbitals in D. So it is 1, 2, 3, 4, 5, 6, 7 and 8. 8 electrons. This is if it is 3d, then we have 4s, then we have 4p. It is like this. Now see what will happen in this particular case over here. We basically know that this Cl is the weak field ligand. Cl is what? Weak field ligand. Now one more thing. See, valence bond theory told us that ligands basically are of two types. One is strong field ligand, another one is weak field ligand. In strong field ligand, pairing will occur. And in weak field ligand, there will be no pairing. So what is happening over here? I am talking about Cl, which is a weak field ligand. In weak field ligand, there will be no pairing. So that means what I told you, according to the valence bond theory, they will provide it vacant orbitals. Now what are vacant orbitals? Vacant are empty orbitals, this orbital. And basically how many Cl? 4 are there. So one Cl will come over here. One will come over here, another will here, another will here. So what will be the hybridization? Hybridization will be sp3, 1s and 3p. What I told you, valence bond theory states us that it will provide the vacant orbitals. So 4 Cl have to come, no? So they will come over here, not here. Not here, because they want vacant orbitals. As you know, in the case of Cl, there is weak field ligand, so there will be no pairing. Hence, we will get sp3 as the hybridization. Now, taking one more example in order to understand it more clearly of the strong field ligand, we can take a case of like this. Let us say that we have nickel and then we have Cn4 and this charge is -2 again. So let us calculate the oxidation number. First of all, for this particular case, we have x plus. For Cn, we know charge is -1. How many Cl? 4. Total charge -2. X minus 4 is equals to -2. X comes out to be -2 plus 4. That means +2. Again, we have nickel as central metal atom. So nickel ground state electronic configuration is what? It is 3d8-4s2. That means when nickel will be present in +2 oxidation state, 2 electrons will go. It will be 3d8. Again showing over here. This is 3d8 electrons. How many? 8. 1, 2, 3, 4, 5, 6, 7 and 8. 7 and 8. Now this is the 4s which is empty and this is 4p which is empty. Now understand this very basic concept. Over here, we are using Cn and Cn basically is strong field ligand. So pairing will occur. What will happen? Here this electron will shift over here and pairing will occur. What will be the configuration? See now. It is 1, 2, 3, 4, 5, 6, and here pairing will occur, so they will come like this, and they are still empty. So now, as per valence bond theory, they shall provide it vacant free orbitals over here. So what will be vacant orbital? Now this is empty orbital, this is empty. How many CN have to come? 4. So 1, 2, 3, and 4. What will be the hybridization? This is D, this is S, and this is P2. So basically what? 2P, 1D, and 1S. DSP2. Now see over here. See over here. sp3, when it will be tetrahedral, and for square planar it will be dsp2. Is it clear to you, students? Great. So you can write it over here. Here we shall get the hybridization as dsp2. Now let us see the limitations. Now while explaining you about the limitations of valence bond theory, we have certain points over here. The very first limitation is it involves a number of assumptions. The second one is that it does not give any quantitative interpretation of the magnetic data. Okay. Now, next is, it does not explain the color exhibited by the coordination compounds, which we shall be observing in the crystal field theory, which is the next theory. Next is, it does not give a quantitative interpretation of the thermodynamic or the kinetic stabilities of the coordination compounds. Great. And the last is, it does not make exact predictions regarding the tetrahedral and the square planar structures of the 4 coordinator complexes. And it does not distinguishes the weak and the strong field ligands. Yes, it tells us, but it does not explain the proper explanation, the reason behind that, which will be explained by the crystal field theory. Now students, there are some of the questions which I will be giving you as your homework, and I want you all to solve it. So the very first homework question is, according to Werners theory of coordination compounds, first option, primary valency is ionizable. Second, secondary valency is ionizable. Third, primary and secondary valencies are ionizable, while D is neither primary valency nor secondary valency is ionizable. So this is your question number first, which is your homework, right? Now the next question for your homework is, filling the blanks. According to Werners coordination theory, there are dash kinds of valency, dash and dash. Okay, and the primary valency of the central metal atom ion is satisfied with dash. So you have been given with certain examples. You can take the screenshot and write the answers in the comment section. Now comes your question number third as your homework. Question third is basically, which of the following primary secondary valencies are not correctly marked against the compound? So you have been given certain questions over here. And next comes your NCERT example question 9.1 and 9.7, and NCERT back question 9.1 and 9.15 is referred for your homework. Yes, students? Okay. So students, today we shall end our segment over here. As I told you, these were the theoretical segment that you will be looking over here. Now your work is to solve the homework questions, to re-revise the topics, and be prepared for the next lecture, because it is as important as this particular lecture. So before ending, I would say one thing: love yourself for who you are. You were born to be who you are, so embrace it. You are a beautiful human. Your unique beauty is yours alone. You have many gifts and talents to share, so share them in your own special way. Your story is yours alone. Use it to help others. Surround yourself with people who truly see your best self. Okay? Shine your bright light on the world for all to see that you are a miracle. Love yourself for who you are. So students, in the process of any examination, in the process of becoming something good, a successful human being, you shall be facing a lot of obstacles in your life. But the one thing that you need to keep constant is the kindness, is the gentleness, is the calmness that you need to hold in yourself, right? You need to be positive in your life. And see, when you feel that situations arises in your life, just be positive, be strong, and say that this situation is not more than my confidence. You know, you are unique, you are beautiful, you are a miracle. So we shall meet in the next lecture. I want you all to read all of these topics again from the NCERT and solve the homework questions and write in the comment section with your name. So we shall meet in the next lecture. Till then, keep smiling, keep learning. Thank you so much and have a good day.